I'm delighted to introduce David Harwood, Professor and Chair of Stratigraphy in the Department of Earth and Atmospheric Sciences. I'm in the soil sciences, not the hard sciences, so I hope I pronounced that okay.
Yeah.
Dr. Harwood has been at UNL since 1990. He's a committed educator, a member of the Teaching Academy of the College of Arts and Sciences, currently serves as the president of the Nebraska Academy of Sciences, and offers impactful field-based professional development opportunities for teachers during the summer. He teaches a course on Antarctic geosciences to non-majors, using the history and mystery of the southern high latitudes as a hook to engage their interest. You might get some requests to audit your course on the other side of this presentation. His research area focuses on the climate and glacial history of Antarctica and the Southern Ocean. Micropaleontology is his research expertise. He's been to Antarctica more than 15 times, leading small, remote, tent-based geological parties as well as large international drilling projects. He's the leader of the Antarctic Science Management Office, which led the International ANDREL, Antarctic Geological Drilling Program, and the Salsa hot water drilling efforts, both of which he will talk about today. David is looking forward to sharing information as well as offering his perspective about Antarctica and this region's connection to the rest of the planet. He will discuss the long legacy of polar research at UNL, its recent project outcomes and their significance, and he'll finish with a bold plan he's developing for UNL's Grand Challenges competition. There will be a Q&A following his presentation, so have your questions ready. Please join me in welcoming Dr. David Harwood.
Hey everybody, I'm really happy to be here to share some of the research that I've been doing, my colleagues and I have been doing, and also to meet you. You know, and I very much appreciate your collective legacy and activity, and the fact that you are all still here working and visiting here shows that I think you were also very active as academics. So in the future, I will be joining your ranks at some point in time. But as you can tell from the commitments I have associated with some of this presentation, that I still have a fair bit to go and to do. So this is going to be a bit of a diverse, multifaceted presentation, again, about some research that's been going on, but also a bit of history of polar research at UNL, which actually goes back more than 60 years. So if we think of a research area that UNL has been a focus of, I think this is one that goes back very far. And indeed, it involved folks at very high levels here. Jim Zumberg was a former chancellor of the University of Nebraska, 72 to 75, days when I was in high school here. He was also a leading Antarctic scientist during the International Geophysical Year, 1957 to 58, which is when many nations got together to figure out things about our planet. At that time, many nations claimed parts of Antarctica, right? And as a result of the International Geophysical Year, the Antarctic Treaty was born, turning Antarctica into one of the first locations of the global commons, if you will. And just interestingly enough, interesting and somewhat timely perspective here as well, that during the Cold War, it was actually the Soviets and the United States. We got together to tell the other nations, no, you're not going to make a claim. We're not going to recognize your claim. And the Antarctic Treaty was born from these two Cold War. So in just thinking about the way that this polar region that we all share, we all own, can also give maybe some vision on the sense of peace and world stability. I used to say, and probably I still do, but up until recent times, I used to say that one of the greatest challenges facing the world right now is climate change, and just with political things going on in the parts of the world right now, there's something that's taking maybe a bit of priority over that, but it still is a very important issue, which I also want to talk to you about here a little bit. So Jim Zumberg, very involved here. He hired Robert Redford, also a geologist, to come and help lead and manage the Ross Ice Shelf project. Maybe some of you knew these gentlemen when you were working here as well. He was also a interim chancellor of the University of Nebraska as well, and also president of this international body, the Scientific Committee for Antarctic Research, as was some. And the Ross Ice Shelf Project, something that went on in the 1970s, we are still working on these materials, and we are continuing this research going on there as well. We've been pioneering stuff back at this time, using hot wire and a flamethrower to make a hole through the ice to get stuff underneath. We're still doing that in advanced our way as well. Sam Trevis, a colleague of mine, also an Antarctic geologist from the Department of Geology or Earth and Atmospheric Sciences. You can see him there. He was research dean in the College of Arts and Sciences for some time, and just some newspaper clippings here, appointed as a department head back in 1964. So again, just to reiterate that UNL has been a leader in polar research for many, many years. Things that I've done since I've come on board here as well have also continued some of that. And with the Grand Challenge initiatives I'm trying to lead and propose, we may take a big step forward in that as well. One project that I led early on was this Antarctic drilling program called ANDRO. 4 nations involved to figure out some aspects of past climate history. We didn't really have a clear understanding about how the ice sheets behaved under past times of climate. And the tagline for this, even the logo there from Back to the movie Back to the Future, is very telling, in that we are drilling back in time to understand what happened in the past. And if it happened in the past, it can tell us something about the future. We can actually learn a lot about the future by understanding past conditions. So just a scene from that Andro project. That's our drilling rig out in the middle of the floating Ross Ice Shelf, drilling down into the seafloor and going through different rock layers. A bit of a cartoon here done by Angie Fox from the University of Nebraska State Museum. But you can see these different color changes, right, are also reflecting changes from the sediments out here to these gray sediments to here, to the gray brown sediments through here. So as we drill down, we've actually seen times like these brown layers, this ice had migrated all the way across, right? And in times when it's this light green through here, all the way across, that means it was open water, open conditions across there. So a schematic, simple way to show that the Earth is having various patterns of change that we can read in the rocks. And just one of the upper part of the first drill hole we did, and each one of these steps is a football field. And we recovered with the drilling rig we had 98% of everything we drilled through. So phenomenal as far as recovering that record. And for the first time, we were able to show that the West Antarctic ice sheet, this ice sheet over here, the smaller one, what did actually come and go in the past. Didn't know that until we produced this record. We knew the ice sheets in the north were coming and going, but by getting these geological records, it gave us a sense of the climate variability. And just seeing these different colors through here, the greens with lots of stones in them are actually ice periods. The yellows are representing open marine conditions like that, similar color coding. So we're actually seeing the ice sheets advancing and retreating. So the ice sheet was very dynamic during this past time. The time period we're looking right here is the time period in the past, maybe 3 to 5 million years ago, when carbon dioxide levels, which drive how warm our planet gets, were at the levels they were today, 400 parts per million. So to give you that example about how what we see happening in the past is a guide to today, we are at 400 parts per million carbon dioxide in the atmosphere today. The last time CO2 was that high, West Antarctica was gone. And it was in this dynamic mode. So if that is a means of predicting what the future will be, we have already bought the absence of the West Antarctic ice sheet at 400 parts per million. So determining what drives whether Antarctica looks like the left side in the cold condition or on the right side over there. And both of these different scenarios have played some roles in the past. So that's a little bit of an introduction. But I wanted this, my smiling face there. I'm actually smiling on the inside. I'm in the Arctic. This was two years ago. And I just want to say I love my job. I love the opportunity to be able to do research like this that's important, but also to convey this to students and the public. So happy to share this information with you. I had the privilege of having 3 summers in a row. I went to Antarctica in 2018 on a drilling ship down around here. I then went to the Arctic, right, in July and August up here. And then I went back to Antarctica over here. So I have a lot of research that I need to be doing, so I'm being a bit busy, but here's a small 4-person camp, my tent right there, in just beautiful landscapes through here. So I want to give you a little bit of a sense about what these environments looks like. I was on this drilling ship. It's an international ocean drilling program or international ocean discovery program now, and spent 2 months drilling on this ship to recover some rock history. And we were a cruise that was actually honoring the 50-year anniversary of scientific drilling. In the same time that international investment, kind of carrying along from the international polar year, geophysical year as well, other efforts for drilling was going on the Antarctic continent, not just in the oceans, but in the Antarctic continent. And a major revolution in our understanding of Earth processes and Earth history came as a result of this drilling ship or its predecessor, the Glomar Challenger, because it proved continental drift, it proved plate tectonics, it proved that the oceans and the Earth is a very dynamic state. So and you can see the progression of various different projects through here, through time. The more recent project when I went to Antarctica was a project called Salsa. And as Antarctic field seasons go, sometimes you don't leave the ice when you think you're going to. So I was actually late for class. Starting my Antarctic geosciences class, finally got back to the station. I was about to jump on that airplane and go home and try to make my way home. I was going to be about a week late. So I emailed all my students and said, okay, don't come to class. I'm not going to be in class, but here's your first assignment. 2 questions. Where's my professor? And then what is the Salsa Project? And it was actually a great opportunity to do this kind of asynchronous learning because they were investigating things on their own. And then they were shooting me questions while I'm standing in line trying to catch an airplane and I'm answering them right this way. It's a really interesting way to meet them in that. But a little bit of background about Antarctica as well. You know, it's a continent. It's the size of the United States, basically this scale here, and Mexico together. It's a huge thing, right? It's got a very, very thick ice sheet on top of it. You can divide it up into 2 different parts. West Antarctica, this lower bit right through here. And then East Antarctica, much higher ice sheet. And they have quite different personalities because the East Antarctic ice sheet is a lot higher, therefore it's colder. The snow that falls on this ice sheet is much colder, it's more stable. West Antarctic ice sheet, you can see, is lower. And it also has a greater connection to the ocean heat. Right? So it's more potential for vulnerability. Also another face to put on the Antarctic continent. This is what it would look like if all the ice were removed. Right? Anything that you see here that's blue would be under the sea. All of these areas through here are presently being pushed down by the ice. They would eventually rise up, but they would initially have seaways coming into them. The dark brown and red areas are mountains. The Transantarctic Mountains splits East and West Antarctica. The Camp Bertsim Mountains is a mountain range no one has seen, but it's about the size and elevation of the equivalent to the Swiss Alps, right? Just an interesting dynamic for that. Maybe to put a better face on that, you can see what Antarctica would look like if all of that land were to rebound after the ice were gone, and you can see it would be a very, very active place, right? So think about, New York City, Houston, San Francisco over there as far as scale for this large landmass. Now, geologists can be time travelers. We drift in our minds back in time. We think about the world, different world states, as well as registering it today. But it also gives us the opportunity to be time travelers into the future. And we can learn a lot by what we see. 20,000 years ago, large ice sheet covered parts of North America, parts of Northern Hemisphere here in Europe, and this ice sheet, they progressively went away pretty quickly. They went away naturally. They went away as a result of changes in the shape of the Earth's orbit, change in the amount of solar radiation that's impacting the Earth because of tilt of the Earth's axis, as well as change in the shape of the Earth's orbit. But a big question we have is, what about Antarctica? How stable is Antarctica? What is its history? What could the future hold for how fast and how big changes in the ice sheet could be? I mentioned that with the advent of the ocean drilling program, that was a revolution in understanding Earth processes. This is the next big revolution in our understanding of Earth processes, and that's the recovery and collection of ice cores very long ice cores from the tops of Antarctica and from Greenland. And it's these ice cores drilled deep into the ice that provide us with a past history of how the atmosphere changed, how temperature changed, and how the Earth works, basically. In the ice, there are tiny little bubbles. As snow falls on the ice sheet, it collects, it gets buried more deeply, and eventually bubbles in the ice and snow get trapped. Scientists can drill deep holes back in time, take chunks of that ice, stick that ice in a vacuum chamber, suck out all the air, and then melt the ice, and then measure the air that's come out of the bubbles. Right? So we have a means of telling past atmospheric changes. And that's kind of what you see through here. This would be today. And the record from the Epica ice core record at the top of Antarctica goes back almost 1 million years. And we can clearly see this almost heartbeat pattern of glacial interglacial cyclicity. Right? High CO2 and warming, and cold times down here of glaciation. And we've come out of the last glaciation 20,000 years ago, because down here, those ice sheets were over North America and over northern part of Eurasia. And we can understand a bit of that history. We can also look at other factors in this, but I really want you to take a look and see that for all of this, almost 1 million years, we've been inside this box. And there have been natural variability of climate change, right? Glacial, interglacial, glacial, interglacial, and now we're way up here, right? We are no longer in a normal world. We are no longer in the natural setting. The history of sea level change and ice sheet growth and retreat is also very evident through here for records from coastlines and some other ocean proxy record as well. But if we think about sea level, how fast, how much, and where is the source of that ice that's melted to cause the sea level to rise? There is no doubt, just from empirical measurements, that the Earth is warming. Each of these is a decade, a single year, and we can see just in this trend of color that the Earth has progressively warmed, right? Across this 1850 to 2018 or so trend, we can clearly see that the warmest periods are in our most recent history. When those large ice sheets were over parts of North America, this was the coastline, because all that water that was removed from the ocean through evaporation was then stored on the ice sheets in those big ice sheets. When those ice sheets melted 20,000 years ago, sea level rose to its present state. It flooded valleys. Chesapeake Bay, Delaware Bay represent estuaries, flooded valleys because of that sea level rise. So the current coastline is really only determined by how much ice is actually on the planet. What's this shoreline right through here? That would be the shoreline if all of the ice in Antarctica and Greenland were to melt, right? So that's kind of the question going into the future. And surface elevation of the ice sheet, very high up through here, maybe 4,000 meters. Large areas around here are floating. And the stability of West Antarctica is a point of interest. Just in the same way that the Northern Hemisphere ice sheets grew and shrank and grew and shrank and grew and shrank through time, the Antarctic ice sheet also was at peak glacial state through here 20,000 years ago. This is actually at the same scale as the previous slide. Right? If you look at some of the edges, but you can see a lot more ice is in Antarctica. The Antarctic Peninsula is very much expanded in terms of its ice as well. And if we look at the pattern in the area that I'm going to talk about here for the Ross Ice Shelf area, we can see that when the ice was at peak flow, peak size, ice was flowing basically north to south, or sorry, south to north. Right? But if we go forward in time and the ice sheets get smaller, we can see that the trends of the ice start to change, and today they're flowing actually across more from almost southeast this way. And that's important for geologists as we're tracking where sediments have come from. If we look at those areas that satellites are telling us where most of the ice is being returned to the sea, we can see that West Antarctica is a very active place. Each of these different circles here represents how many gigatons of ice are lost. Some parts of East Antarctica are more stable, but West Antarctica is pretty dynamic and vulnerable, right, and showing some changes. On this side over here, we're actually seeing temperature of the ocean. And in the ocean, because of the salt, it freezes at around minus 1.8. degrees, almost 2 degrees, minus 2 degrees C is when the ocean will start to freeze. And the sea around Antarctica freezes seasonally. What you're seeing right here are temperatures that are much warmer. These are still moderate, but they are at 200 meters depth, 200 to 300 meters depth. So a huge amount of heat, 4 degrees almost, right? 4 degrees centigrade, about 8 degrees Fahrenheit, is just below the surface. And that's what we're looking at, is trying to figure out how that heat could potentially destabilize and interact with the ice sheet. Before we drilled with the Andril record, we didn't know that. Modelers, numerical modelers, tried to make the ice sheet grow, and eventually they could do that. They tried to make it go away, and they couldn't. The only way they could if they introduced ocean heat. So it's melting from below. It's becoming destabilized from below. So the drilling that was led out of here at UNL led to focus on this ocean heat. And actually look over here, all this heat, it's just on the edge of Antarctica over here. So anyway, it's the current way we're trying to understand what can go on. And that heat that I mentioned in that warm water mass, which is just 200 or 300 meters below the seafloor, it's this circumpolar deep water coming from the North Atlantic, making its way here and then flowing around Antarctica. But there's a huge heat source, not melting from the surface, but actually melting from the ocean heat below are some of the questions that we have. When I was late for class, I was actually part of this project, being a scientist, but also managing and working with the drillers that we hired here at UNL. This is actually UNL's largest hot water drilling system. Each one of those is a 40-foot container. It's basically the equivalent of 6 car washes, right? That provides the power and the heat to melt this ice. And had about 50 people at camp, that's our tent, and some various sites through there. We drilled 300 feet down, 1 kilometer down with that system, and we entered into a subglacial lake. Pioneering research, there are actually abundant lakes underneath the Antarctic ice sheet. Every dot you see on this figure right here represents a subglacial lake. The largest one here, Lake Vostok, is almost the size of Lake Ontario. Right? They're freshwater, yeah, freshwater. And they're coming from, you might say, well, why it's so cold, right? Why is there meltwater underneath the ice sheet? But ice, right, with pressure, it melts, and you have all that geothermal heat radiating out as well. So the ice is actually an insulating blanket for some of that. One of my colleagues indicates that the Antarctic ice sheet and the Antarctic region is actually the largest wetland on the planet. We just don't see it, right? So we wanted to sample this. The reason to sample it, chiefly funded by National Science Foundation and some other international involvement as well, was to understand the microbial ecosystem, the viruses and the bacteria that work in this system. And the UNL team drilled in 2010 over here. They drilled over here in the Salsa Project I'm going to talk about in 2018-19. And in the first project, they recognized 3,000 different types of organisms by their DNA spectrum, right? Next valley over, they identified 300. So an order of magnitude less from one valley to the next shows you that we don't really understand a lot about this particular environment. We can actually think about this in terms of river systems and lakes. And actually, all of these represent lakes in this sector where we were drilling. And they were first identified by satellites because the surface of the ice sheet, it's rising and it's falling. It's rising and it's falling. As people scratch their heads, how could that be? But it's because water's flowing under there and the water has nowhere to go, so it is lifting the ice sheet up. These lakes are filling and draining and filling and draining. Think about a big plastic sheet, like a slip and slide, if you will, right? And you got a big hose under there filling it. There are going to be blobs of water that are going to raise the surface of that plastic sheet. Similar thing is going on here. And to give you a sense about how big these things are, this is Subglacial Lake Mercer, where we drilled, and here's this pattern of elevation changes and velocity changes to identify those. But if we put Lake Ontario in here as well, those are at the same scale. And up there, almost the same, right? Maybe this is twice as big as Lake McConaughey, right? Just to give you some sense about how big that is. I want to share with you a short video of a videographer who went down with the team for this and was able to present some of the information about this project to the world. And it's currently running the circuit of a variety of different film festivals through here.
just doesn't make sense that a continent this big has no life. Next week, we're going to be drilling a hole through 1,000 meters of ice, and we don't even know what's under there. Isn't that exciting? Might not even be water there. Holy crap. You know, I mean, we're going in totally the unknown.
I think there's just something about going to the unknown. It's nothing like what you really think it is. But when you get to the field camp, that's when you really find out what it's like to work in Antarctica.
Sweet home.
When you have a continent that's almost completely covered by ice, and all that ice has the potential to melt and raise sea level, you certainly want to understand its history. And some of those clues are held in the lake sediments.
There's the basic science curiosity aspect, too, of knowing how and where life exists on Earth.
If we do the best we can, we're advancing science, I guarantee you.
3 a.m. playing with mud, living the absolute dream.
So this is all dairy farm stuff. Hey, when you hire farmers to build your drill, that's what you get.
It's a complicated mechanical system that, if it breaks, you're in the middle of nowhere to fix.
You never know, it's Antarctica. It can always bite you.
We're apparently stuck on something.
We got to get this out of the hole, but we can't use the hole at all.
This is dangerous, right?
We're gonna lose this if you don't careful. Yeah.
We have a very limited amount of time. You only get one chance.
Showtime. Everyone thought it was this big, dead, benign block of ice.
That is way different than I pictured it.
But there's some big lakes under this ice. Some of the largest lakes on our planet are under this ice. And we just have to get there.
I hope that gave you a little bit of a sense about Antarctica and the environment. It's cold, but it's no colder than February out here, you know, when you get a cold session. You saw those glowing kind of blue lights, that's ultraviolet radiation. So anything goes down that hole, we make sure we bombard it with really intense ultraviolet radiation so we're not introducing any microbes into that system. And a lot of filtration as well that goes on. So a couple of spots have been drilled already, the one I'm talking about right through here. But there have been other efforts from hot water drilling, from our team and the New Zealanders chiefly, in this area as well, to try to understand what's going on with this area. What is the stability of West Antarctica? We actually took some sediment cores. We sampled the water. We did a lot down there. And this is a kind of a profile of the cores that we collected. It's about 2 meters in length. There's a lake phase through here, then the ice touched down. There's another lake phase up here, and we can actually see in the layers through here times when the lake was draining and filling. So we can tell the past of what's going on in some of these. And my role in this project scientifically was as a paleontologist. I study one-celled algae called diatoms. I use these to date sediments, date times when marine seas covered West Antarctica, and also interpret some things about the past environments. So here's some of the creatures that I studied. So with the andro cores that we drilled, really long, kilometer depth of cores, we want to extend that record, which was showing the ice sheet's variability. We want to actually get into the heart of West Antarctica, right up under here and up in here to collect some samples. And we have some various spots through here. The next project we were just funded by the National Science Foundation, kind of a continuation of the andro approach. We've almost tripled the number of nations that are involved in this now, and that's a proposal that we will drill this hole this coming autumn. And then we'll drill this hole the next year to get right into the heart of that. And we can see from some more of these diatoms, different geological times are represented. So each time we have fossils of those ages is telling us a time when West Antarctica was open marine. And again, if it's happened in the past, it can happen in the future. Right? So how recent, how fast, how dynamic has some of this history been? And these are those same images that I showed you before, and they have relevance through here now because we're trying to see where different ages of fossils have been transported underneath the ice, coming this way or coming this way. And interestingly enough, it's only those samples that are coming more from this sector over here, which we think are derived from this area, have younger diatoms in them. Those that are back here don't have them. And those out here don't have them. So it's giving us some sensitivity of the ice sheet. We thought initially that this would be an area that would become marine first. That's over here. Or this area up here, the other side of West Antarctica, would become marine first. And that's what our initial models that came from the Andro project showed. Those were sensitive areas. At 400 parts per million, it's going to go away. And we thought the ice went away coming this way and coming this way. And now the new models and this new information shows that's not the case. This is a far more vulnerable sector, the Thwaites sector. It actually comes in here earlier than this. And indeed, our more recent history is showing that this was active, coming and going, when these stayed stable. Just got some samples here from the British Antarctic Survey. I looked at those, and they're also stable through these younger times. So it's kind of bearing out some of this history. But by drilling in these areas, we'll hopefully get more of that pattern. But it's a bit scary. I am frightened. I'm frightened by how fast everything that we get, every new bit of information we have, every new numerical model that we develop that is tested against the past to have it improve, it just gets more and more rapid and more sensitive, more and more vulnerable, right? Nothing goes the other way. The more we know, it's kind of problematic. And this is why some of this is important. It comes back to this ocean heat. And particularly this sector over here, the Thwaites sector. Here we have ice grounded below sea level, and we have open ocean water, sea level somewhere around here, and the glacier's stable if it gets stuck through here. But if sea level starts to rise, and warm heat starts to come in from the ocean and starts to melt this up, the reverse slope of this gradient just causes the ice sheet to collapse. Right? It's not stable, particularly because of this reverse bed going back underneath the ice sheet. Most other continental shelves around the world, they prograde outwards, right? Progressively getting deeper. This one's the other way because every time the ice advances, it plows out more material. Right? So kind of unique and also very sensitive. And here's where some of the subglacial lake work comes out, because are the subglacial lakes episodically draining? Are they purging? Are they sending out fresh water at various times? And if they are, right, it should be that pattern of the subglacial lakes draining, fresh water floats up, and as it floats up, it pulls in this heat. It pulls in the other waters to replace it, causing some further patterns. Antarctica today is cold. It's dry. It's actually the largest desert on the planet. You wouldn't think about that, right? There's no runoff. There's no meltwater from the surface because it's so cold. But the meltwater is coming from underneath. And this is something we're just starting to visualize and understand as well. So not only is this fresh water coming up, causing warm water to come in, but nutrients are actually going into the ocean. And the fresh water is actually feeding the coastal areas. This is chlorophyll. So you're actually seeing more productivity of diatoms and other things close to the continent. So the more fresh water we have, the more we put in new water into that, the more productivity we're having here. And that might actually buy us some time because the more plants grow, the more they're buried, the more carbon gets sucked out of the atmosphere at some point in time. A few more minutes here, if you could so oblige me. The next project was just funded that we're going to drill this season, led by the New Zealand drilling team as such, is to drill these two holes right through here. It's with a new drilling system. All these different nations are involved. I think everybody's young here. That's just because I'm old, right? It's just kind of the way that goes. But looking at this and combining the funding sources, not just from the ocean drilling program, but the International Continental Drilling Program, plus the individual nations, scientists, myself included, proposed to fund this project. And it's a little bit washed out here, but this is a cross-section across West Antarctica from this side to that side. You can see the big ice sheets across here. Go to a next stage here, modern sea level, right? The ice sheets here. And sometimes in the past, the ice sheet was just in the center here, and West Antarctica was mostly open marine. So we're trying to drill here and here to get the history of what things were like back then. And here's kind of a concluding slide for all of this. And again, the Scientific Committee for Antarctic Research, one group that's a sub-study group, focus study group of this is called PACE, Past Antarctic Ice Sheet. The next one is called Instant in this, but it's trying to focus on these problems. But it's chiefly using data from drill holes, from the ship, from andro-like things, or from even farther inlands, and then that information feeding into the numerical models to get a history of what happened in the past. If the models are improved enough to tell what and recreate what happened in the past, then they're good enough to predict the future, right? So the models improve by being tested against these records we're developing, and then they can help predict the future. It's kind of this way with the ice cores and the drill cores through past warm periods, et cetera. Then the models get better in trying to recreate this history. And if the models are better, they can then predict at CO2 levels rising if we do nothing, what's going to happen to the Antarctic ice sheet. And this is a future space here. Or if we start to turn things around and we get to these CO2 levels by 2020 or so, what's this going to look like? To further our ability to do this type of research, Jim McManus from the College of Engineering and myself, and doing this hot water stuff, it comes to this grand challenge, this grand idea of how can we do better science? How can we work in this environment? And the tagline you see down there, Cold Region Science and Education in a Cold War Facility, kind of plays on this. And the timing probably couldn't be any better than this. This is a new drill that we're trying to get funded to build it. Oftentimes drills from the surface are powered by rotation, right? We're trying to do something different. We have a hot water drilling system. It's 6 car washes. It's powering this thing. You don't get an attenuation of energy with hydraulic pressure. So we want to actually drive the drill with water coming from the surface. You can melt your way down, but then this new device here would be powered by the pressure to rotate, or the pressure would drive a turbine, which would generate electricity, and then we would use electricity to power a motor, which would then drill through that. But here's the big question about this. Well, you can see some of that. This tool would actually go through dirty ice, go into the sediments. It'd be one-stop shop for this tool. But here's the thing, is where do we test it? When we're going to propose to build this, we would propose, I don't know, $300,000 to $500,000, $300,000 to $500,000 to go to Alaska, to take our hot water drill up there, to do all this, and then test it and see how it works, right? Or we could build something more locally and test it locally, right? So how is this related to the grand challenges? Where do you test this thing? There's a missile silo in Seward, right? Which is a huge, big hole. The only similar type of cavity that we can drill through, fill it with water, is in Wisconsin. It's about this diameter, right? And it is fill it with water and then drill it. Maybe it's 30 feet deep, and that's it. But imagine a 20-story building underground where we actually can custom build, like Minecraft, a game. You build a block of ice, plug it in, build a block of ice, plug it in, and you can customize what you're going to drill through. We could actually set up a scenario that we're proposing to drill in the future that would be marine sediments, and then glacial sediments, and then actually a water cavity we would have to go through and enter into then dirty ice, and then on our way up. So we could custom make whatever we were going to do, and we could do it just next door, right? Be a great place to instrument our tools we're building, but also to test and calibrate them in some way. Proposed this and brought in a lot of other colleagues from around campus, because the great educational opportunity is here as well, not just from history and Cold War, science literacy, and a variety of things like that. But here's the site. It's in Seward. It's 20 acres of sort. Imagine having up here a sculpture garden with science components or sustainability, right, or peace as the themes. There's the drill. There's the site right there, the silo. That's the entrance to it. Education facilities, education tours, some other opportunities through here, and I'm running long here, but that's what's coming next in trying to advance in a big way what we've already done for 60 years of research and polar activities for this. This is 1961. They built 12 of these around Lincoln in a year and a half. They built 84 of these around the country in a year and a half, and only operational for about four years. Anyway, thanks. I appreciate your attention for all this. I do enjoy what I do, and I'm really happy to share with all of you. Yeah.